All right, this is the third example problem in the curve sketching series of videos. Let's sketch this function. So step one is we find the domain. So you can input any x into this function except for an x that would cause the denominator to be equal to 0. So we can rewrite this. If we factor this x squared minus 4, x can't be minus 2 or positive 2. But any other x is fine. So the domain is minus infinity to minus 2, and then 2 to infinity. And then the range is all real numbers. Okay. Now the intercepts. What are the y-intercepts? Let's set x equal to 0 and solve. So you get 0 over 2 times minus 2. So the origin is an intercept. Okay, now the x-intercepts, set y equal to 0 and solve for x. So x is equal to 0. So the graph only intercepts the x or the y axes at the origin. All right, next we test for symmetry. Is this an even function? So y of minus x is equal to, and this is not equal to y of x, so it's not an even function. What about an odd function? So what is minus y of x? This is, and this is equal to y of minus x, so this is an odd function. Okay, now is it periodic? Is there some number p to where if you do y of x plus p, you get back y of x, like a trigonometric function? No, there's nothing you can put here to replace x with x plus a number that would result in the original function back. All right, now let's do endpoint behavior. Take the limit as x goes to the endpoints of the domain, so minus infinity and infinity. Okay, well, this is a rational expression where the order of the numerator is less than the denominator, so we know that this limit is equal to 0. And same idea with the limit as x goes to positive infinity. All right, next step, let's get the critical points, both with respect to the first and second derivative. So critical points, first derivative, okay, let's solve for where this is equal to 0. There are no points where this is equal to 0, but there are 2 points where this doesn't exist. X is equal to 2, and x is equal to minus 2. Okay, now the second derivative. Okay, so critical points are x is equal to 2, x is equal to minus 2, and x is equal to 0 with respect to the second derivative. Okay, next we want to look for asymptotes. And to do this, we take the limit as x approaches all of the critical points from the left and the right. So -2 from the right. -2 from the left. So the limit of E with respect to x approaching -2 from the right or the left. Oh no, we would do -1. There we go. So negative infinity. Okay, now from the right is positive infinity. Okay, the limit as x approaches -2 from the left. Is negative infinity. And then -2 from the right is positive infinity. Okay, now when it comes to x is equal to 0, we know that y of 0 is equal to 0. So it's continuous at x is equal to 0. So the limit approaching as x approaches 0 in general of y is equal to 0. All right, next let's get the increasing and decreasing intervals in the intervals of concavity. So the function can only change, the first derivative can only change across a critical point. So we just need to check these three regions. Okay, there's the derivative. We'll call this f. So f with x equal to -3 is negative. So it's decreasing in this interval. All right. With x equal to 0, it's also decreasing in this interval. And then it's also decreasing in this from when x is greater than 2. So it's always decreasing. All right, what about concavity? All right. Call this G. So G with x equal to -3 is negative. So concave down in this region. Okay, that's inconclusive. So let's see. Oh, no. Yeah, because this is another point of that was a second critical point. So we need to say, so -1. So it's concave up in this region. Concave down in this region. And concave up in this region. So these are all inflection points. -2, 0, and 2 are inflection points. And there's no local maxes or mins. Okay, let's sketch the curve. We can start with the endpoint behavior. So approaching positive and negative infinity, it's approaching 0. But is it approaching 0 from the top or the bottom? So to check that, we can say, so the equation with the function with x is equal to, let's say, 100. So that's positive. And then we're about negative 100. So that's negative. Okay. So the endpoints will be doing like this. All right, let's add in the vertical asymptotes. We can see that -2 and 2 are vertical asymptotes. So the axes will go from -10 to 10 and 6 to -6. All right, -2 and 2 are vertical asymptotes. As x approaches -2 from the left, the function goes to negative infinity. -2 from the right, positive infinity. 2 from the left, negative infinity. 2 from the right, positive infinity. This should be +2. There's no local maxes or mins. There is a point where the second derivative is equal to 0. At the origin, this is an inflection point. So we're going from concave up, concave up, concave up, and now we switch to concave down. And that's the only point of significance. So there's no local maxes or mins. There's no other inflection points. So all we need to do is connect here. Like that. And that's the graph. So let's check everything. So again, the endpoint behavior is satisfied. The asymptote behavior is satisfied. But then we see the function is always decreasing everywhere. And then here, we're concave down. In this region, we're concave up. Then we switch to concave down. Then we're back to concave up. So that's the graph of the function.